All right. Good morning, everybody. We are down to the last, 8 classes now. There are 4 this week, and then technically there are only 3 next week because the last day, next Thursday, is our final exam. So we only got like 7 lectures left, and then we have 1 final at the very end. So we are pretty close to the end. So yeah, we are. Well, I certainly hope that we'll be ready for a final exam by next Thursday. This is kind of the an interesting aspect of a summer class. Basically we are compressing 16 weeks down to 8 weeks. The good thing is we are not losing any day to holidays, because in a normal semester we usually lose multiple days depending on what day we meet in the class to holidays. But with a summer session, especially when it's online/remote, we are not losing any days or losing any time because of that, which is a big plus because I usually barely have enough time to go over all the topics that I need to go over in this class. Cool. So the yes, I will remember to post the exam 1 scores. Exam 2 scores are not ready yet. I just worked on the key yesterday. So if you want to look at the key to one of the many variations of those questions, it is in the exam 2 text channel. There's a link in that channel, the last one. It links to a Google document, of my solution to one variation of all the different questions. I don't even know how many variations there are, to each of the questions. I think in some of those questions they are unique, in the sense that everybody has a slightly different question, and in some of the other ones, it's kind of like I think there are like maybe 8 variations for the entire class. So some people may share the same version of those questions. All right, I think it is 9 o'clock. In fact, it is 30 seconds past 9 o'clock. So I'm gonna get started here. The important part is to go back to the stack operations. I didn't really get a whole lot of questions about this one. And there are several ways to answer the questions. The one that asks about how many bytes were used on the stack. So let's go ahead and check this out, because I think it's good to review how to use the CLI, the command line interface mode of of Logisim, in order to run the program. So I'm gonna skip a few questions. I'm gonna skip all the way to the last one, because it's the last one that matters the most. All right, so here's the program. It's recursive. Okay, so how do we know this program is recursive? It really has to do with how we are calling and how we are returning. So the way we are calling is right here. Okay, so the way we call the subroutine is basically from here to here. That's the call to the subroutine called sub1. And someone asked me about what is a subroutine, and it's kind of interesting because when I was in college, okay, the name that we give to subroutines is, well, I guess it's a subroutine, right? In Pascal, it's called a function when it returns a value, and it's called a procedure when it does not return a value, and that's my first programming language. In C and C++, they're simply known as functions. But in some of the other types of programming languages, they're also known as subroutines. And when you declare or when you define a subroutine, you have to use a keyword of sub to indicate that what is following is the definition of a subroutine. So I'm going to consider all of these terms somewhat equivalent in this class. So when we talk about a subroutine, when we talk about a function, or when we talk about a procedure, they are all basically the same thing. Okay. All right. So getting back to the sample program here, this is the call, and then the return is all the way over here. All right, so the subroutine definition of sub1 is in here, and the way subroutine 1 or sub1 does something is really to check whether register C is a 0 or not. If register C is in fact a 0 already, it will skip to this label over here where it returns right away. If not, it will decrement the register C by 1, and then it's going to call again. So when you look at this particular sequence right here, these 5 lines, that's another call. So sub1 is actually calling itself when register C is non-zero. Well, okay, first of all, it would decrement it by 1, and then it would call itself, because otherwise, it would keep calling itself until the stack runs into the code portion of a program and kills the program because of that. So this program does not kill itself, okay, because we decrement first. So there are several ways to answer this question: how many bytes are going to be in use on the stack when we run this particular subroutine? The first one is to just run the program and watch the stack pointer change. And then the second one is to just analyze the code without using Logisim to figure it out. So the question is, how many times is the subroutine going to call itself before it stops and then starts to return? The answer is actually 4 times. The first time is being called from main, and then the other 3 times are from sub1 itself. Because what we can do is to monitor the value of register C, because register C starts with the value of 3 because of this line over here. And then every time we do, right before we perform the recursion, we decrement C by 1. So that means the value of C goes from 3 to 1 and then 0. Now when it gets down to 0, then it starts to return. So we can answer this question just by analyzing the code here, if you can recognize certain patterns, and the answer is 4. Okay, it takes up 4 bytes on the stack. Okay, now specifically this question is asking how many bytes are used on stack during the following program that calls a recursive subroutine. So we are not concerned about how long this particular program itself is, but how many bytes on the stack it's going to use up. So that's one way to answer the question. The other way to answer the question is to copy and paste the code into the assembler, and then we take the code and run it on the command line. So this is what we'll do next. So here's the assembler, and then we go to the source tab. Get rid of all the content in column A, and then just paste the whole program in. Make sure there are no errors. Then we go to the RAM file tab to download. Alright, so when I download, I always download the CSV version, even though it doesn't really matter whether it's a CSV, comma separated value, or TSV, which is tab separated value. It really does not make any difference. But just so that I can easily remember which one is which one, I always download the RAM file as a CSV, but when I generate the log file, I log it as a TSV file. So I'm just going to call this program stack.csv. And apparently I got one already, so we'll go ahead and replace it. And then we start up Logisim, but this time on the command line. Because if you run Logisim in GUI mode, it's not going to be, you can still see it. It's just not as easy, and you cannot go back and analyze the program like you can, in this case. So let's go ahead and do this. Okay. And then we specify dash tty table dash load, and then the name of the file, which is stack.csv, and then we redirect the output to stack.tsv. So one thing you can remember is T stands for trace, okay, which really is not the case. T actually stands for tab, but if you want to remember which one is which one, then when you see TSV, it is a trace. There we go. So now we're done with the tracing, and we have to switch back into the trace analyzer. So let me pick up the folder first. There we go. And this whole procedure of using the trace analyzer, I know it sounds really kind of tedious, okay, if not anything else, but it is actually quite useful because it gives you a vision or an inside view of what happens when a program runs. So here's my TSV file. Remember to replace current sheet when the sheet is sheet 1, and then we force it to use tab as a separator and do not convert numbers. And then we click import. And it takes a little bit of time depending on how long the trace is. The longer trace is, the more time it's going to take for the analysis phase. So now we go to the analysis tab. So I just want to see if any one of you remember, what is my stack pointer? How do I see changes to my stack pointer? Not the stack, just the pointer itself. Can anyone tell me which column I should look into? Yep, alright, very good. Register D is correct. And which column should I look at if I'm looking at changes to a register? If you look at the header of the columns, you should probably get a good idea. Yep, register change. So that's column D. So what we'll do is we look at this column and then we figure out how the register D is being changed. So we can see it's changed here. And if you want to fast forward and not having to scroll and then eyeball the whole thing, you can actually use the find feature. Your controls, I think it's Control H. I'm not sure whether it's Control. Yeah, there we go. Control H will pop up the find and replace, and then we are looking at D equals 2. Now that might also pop up D equals. No, that won't. D equals won't show up. It will only show up D equals 2. But it can potentially show up, when the location also has a D equal to, because this is basically just saying if any cell has as a subpattern D equals to, it will pop up. So if you want to just really kind of focus on the register D, then you can use search using regular expression. And when you use regular expression, the caret symbol, which is shift 6, is representing the beginning of a cell. So now we're basically saying, if a cell starts with D equals 2, then tell me about it, okay? But if D equals 2 is somewhere in the middle of the content or the what they call displayed value of a cell, then we can just ignore that if it's not at the very beginning. So we go find, it doesn't find any one of those. So did I just goof or? There we go. There we go. So if it does find all of these, so the lowest it can get is to go to FD. Because from that point on, the stack pointer goes back up again. So you can count how many bytes are actually in use on the stack. FF, FE, and then FD. It's only 3 times. Why is it only 3 times? I was expecting it to be 4 times. Alright, so I think I just missed one. Yep, there we go. FC. I just missed it, because when I click the find button, I wasn't paying attention on the other side. I was just paying attention to this side. So yeah, so FC is the lowest location because we cannot find the FB anymore. It went from FD to FC, and then from FC it goes back up again to FD. So the lowest the stack pointer got was FC. Now remember, the stack pointer points to the actual thing that was last pushed on the stack. So when the stack pointer is at FC, which is here, that means we are actually putting something into that location FC, which is indicated by column C. So column C is saying that we store a value of 16. Now this is not 16 because it's not a base 10 number. This is actually 16 in hexadecimal. That value was stored at location FC on the stack, which is also in memory. So now we can count the number of bytes. We have FF, FE, FD, and then FC. So 4 bytes are actually used on the stack. So the observation of the trace analyzer is consistent with what I predicted earlier. So this is all good, okay? Meaning that we can actually figure out the answer to that particular question by either running the program, or we can just analyze the code, which takes a little bit of work because you first have to be familiarized with what a call looks like, these 5 lines, and what a return looks like, which are these 3 lines. But the very same lab actually talks about that. So this really should not come as a big surprise. It's just a matter of are you absorbing the information? Are you understanding the concept so that when you see something like this, you can apply what you have learned, and then you go like, oh, okay, I recognize this is a call and this is a return. So Martin is typing. I'm gonna wait for his question. How do you count the number of bytes again? Okay. So the stack is at the very top part of RAM, and if I go back to the trace analyzer, there are several ways to figure that out. Okay, so if I look at the RAM right column, which only records when we put something on the stack or into any memory location, I should say, we find that it's putting 0B into location FF, then it puts 16 into location FE, then it puts 16 into location FD, and then it push 16 into location FC. And then all the subsequent operations, there are no write operations anymore. So if you really just count not the number of cells in column C, but count the number of locations actually being written to, which in this case turns out to be the same. There are 4 occurrences. That's why I can figure out that 4 bytes on the stack were used during the execution of this program. Is that okay? Okay. If we need more time to process this, we can do that. I just need to get some feedback from the class. All right, cool. Thank you. Thank you. All right, so this is all good. So let me continue with today's topic. So what we'll be talking about today is how do we pass parameters, and also how do we return values. So those are the two new topic, in addition to how we call and how we return from a subroutine. How we call and return from a subroutine, that has to do with passing control over to a subroutine and have the subroutine to continue execution in the caller when it's all done. But it has nothing to do with how do we pass data or information into a subroutine, or how a subroutine is going to return that data or information back to the caller. So at this point, this is all about the agreement between the caller and the callee. So let me go back to the class site and kind of point out what module is particularly useful when we get to this point. This is I think it's a module. It's not a module. It is just HTML text that I typed up. So the caller and the callee agreement is basically saying, when in the code for the caller and the code for the callee, what can they assume from each other? That's basically the agreement. So they both have to agree that register D is the stack pointer. Now this one is specific to RISC type processors, because CISP type processors typically have a dedicated stack pointer, so it is usually quote unquote understood without having to make the agreement explicit. In the caller, we push the return address. The caller is responsible to push the return address and continue execution at the start label of the callee, which is the subroutine being called. At a subroutine, the way we return is we quote unquote pop the return address, which is to retrieve what the stack pointer is pointing to, and then deallocate that location on the stack. So when we talk about the return value is in register A, and this has to be agreed upon by both the subroutine that's calling and also the subroutine that is returning. So we immediately have a question. Can we use register C or register B instead of register A? We kind of know that register D is already used as a stack pointer, so we cannot use register D for this purpose. But then the question is, well, can we use any one of the three registers? The answer is actually kind of confusing. It's yes and no. The answer is yes, assuming both the caller and the callee agree on that for the entire program. Okay, so if you say I like register B better as a return value register, then you have to stick with that for the entire program. Okay, you cannot just say sometimes I use register B and other times I use register A, and yet some other times I use register C. So you have to be consistent. Pick whatever register and stick with it. Okay, and the answer is no, in the sense that in this class, because I'm teaching it, so I get to set the agreement. So the agreement that I'm setting is we just use register A. So now the question is, well, but is that reasonable to use register A? As it turns out, even in the Intel architecture, when you compile a program into assembly code, turns out that they also use quote-unquote register A as the register to specify the return value. So I'm not going to get too much into the detail of the x86 architecture, but it does have what we know as a register A. But register A in that sense is not a general purpose register. In fact, it has register A, B, C, and D as well, just like in the toy processor that we are using right now. But in the toy processor, registers A, B, C, and D are really truly general purpose registers. Whatever you can do with register A, you can do with register B, C, or D as far as the instruction set is concerned. However, the way we use the registers, when we're dealing with a quote-unquote C program, is now restricted. Register D is always going to be the stack pointer, and register A is always going to be the register to specify a return value. And Catherine is typing, so I'm going to wait a little bit for the question. In the case of an Intel processor, register A, that A actually comes from accumulator. Alright, so the question is, if I'm using register A for return values, then I cannot use it to store anything else. Well, the answer is once again yes and no. Until you get to the very end of a subroutine, in the callee, the subroutine being called, you can actually use register A just like any other registers. It's just that when the subroutine is about to get back to the caller, then you can only use register A to specify the return value. But any other time during the execution of a program, it's up to you. If you want to use register A as a scratch register for some computation, it's perfectly okay. It's just that at the very end, then you have to put the return value into register A. All right. So so that's the return value specification. Let's go take a look at a very small program, just so that we can get an idea of how to write a subroutine that returns a value. So let me switch back to the command line so I can actually I can write some code to illustrate it. So dash uppercase O means I'm splitting vertically. No, I'm actually splitting horizontally so that the two windows would be side by side in Vim and Vim. The first one is in C, so we'll say return value in C, and then the second one is return value in TTP-ASM. TTP-ASM. The extension, once again, is important if you want to use the syntax highlighting file that I have provided. I really kind of doubt anyone wants to do that because it's actually not that easy. Anyway, so if I want to use int 8_t as a return type, that simply means it's an 8-bit signed integer as a return type. And let's just call the subroutine f, and it takes no parameters. Okay, and all it wants to return is a very specific value. So let's say it just wants to return the value of 61, and don't ask me why 61. I just pulled a random number from thin air. Okay. The question is, for a very simple subroutine that looks like this, what is it going to look like in assembly code? based on the assumption or the agreement that we just talked about. So we'll go ahead and type F as an entry label. And Catherine is typing something. I'm going to wait a little bit because otherwise, the lecture will become very asynchronous. Okay, the question is, what if you just declare the variable as int? I could just do int, but the toy processor can only have 8-bit built-in types. So anything that's longer than 8 bits or wider than 8 bits is quote-unquote composite, which means I have to do something special to deal with it. So in order to make sure that we understand the two programs are truly equivalent, I want to restrict myself to only 8-bit wide integers. So that's the only reason why I restrict myself to int 8_t instead of just an int, is so that when you look at the left-hand side, the C code, and the right-hand side, which is the assembly code, they are truly equivalent in this case. All right, cool. So we have to specify the return value first, and then we actually perform the return operation. So to specify the return value, okay, based on the agreement, now we don't have a caller in here to make use of the return value. We are only looking at the definition of the subroutine that returns a constant of 61 in this case. So to do that is really as simple as this, okay? So we basically specify 61 as our return value, and that's it. Okay, as far as specifying the return value, this is it. Okay, now we have to specify the code to actually return control to the caller. Now the caller is not in view, but remember there's a hidden agreement between the caller and the callee. F being the callee is making the assumption that the last thing that the caller pushes on the stack is the return address. So that means I can do a LD. Now I cannot use register A because register A is now being used as a return value. So I can use register B or register C at this point. Pick one, okay? It truly is not important which one you pick. So I use register B, and I just say whatever the stack pointer, which is D, is pointing to, put it into register B. Now that I have retrieved what is being pointed to by the stack pointer, I don't need the stack pointer to point to that anymore. In other words, I can free up that space for other things that I may want to store on the stack. So I increment the stack pointer, and then I can use a JMP-B without the I, so that I continue execution at the location B that B is specifying. So this line here, okay, let me turn on line number here. So line 2 is specifying the return value, and then line 3 to line 5 are specifying the instructions to actually continue execution in the caller and clean up the stack at the same time. Okay, we only clean up one thing on the stack, which is the return address, where we are supposed to go back to. So the confusing part about this is these 4 lines, lines 2, 3, 4, and 5, are implementing that one single line of return 61 in a C program. Because in the C program, when you say return, you're actually saying two things at the same time. You're specifying the return value, but you're also specifying that I want to go back to the caller now. Okay? And that's why it can get a little bit confusing sometimes, when we translate C code into assembly code, because we have to specify in assembly code, they are two separate things to specify. Okay, the return value and the continuation back to the caller are two separate things. Okay, the first one is done by line 2 in the assembly code, and then the second one is done by line 3 to 5 in the assembly code. But in C code and in most modern programming languages, it is done by a single line in the high-level programming language. There are a few exceptions. I think Visual Basic is an exception to that case, because when you use an assignment to change the value of the name of the subroutine, you're specifying a return value, but it doesn't return to the caller right away. And Pascal, I believe, is like that too. Okay, I haven't used Pascal for many years. So there are some exceptions to the rule, but when you look at most modern programming languages like Java, C, C++, PHP, Node, which is JavaScript, Python, they all basically combine the return value specification and the actual action to continue execution in the caller into one single statement. And Richard is asking, so B hosts the address that was stored in RAM bracket D, which means at location D in RAM, yes, which the program will then jump to. That is correct. Okay, so now that we know how to return the value, let's go ahead and take a look at how we specify parameters. Okay, so if you remember from the sample program that you turned in this morning, we were using register C to communicate between the caller and the callee. Okay, but that's a very special case. Okay, in general, we do not use registers to communicate. We do not use registers to specify the parameters. And the question is, why not? Because it's kind of convenient, right? And it's also really fast. The problem with using registers to communicate to pass parameters is we only got 4 registers. The toy processor, being a toy processor, only has 4 registers. We're using one up just for the stack pointer, so that leaves only 3 registers left. Which means if we only want to use registers to pass parameters, that means we can only pass up to 3 parameters, which is not good, okay? Because a lot of routines can take, there's no such thing as a hard limit of how many parameters you can specify for a subroutine. So that means we cannot use that approach. We cannot use registers to pass parameters. Now that is all both yes and no. I'm not going to get into the details of that, but for optimization, some compilers make an assumption that the first parameter is always in a register. So it is okay as long as that agreement is observed all the time consistently by the caller and the callee. So in this class, we are not going to make that assumption. Okay, in this class, we are assuming that we do not use registers to pass parameters. So now the question is, if we are not using registers to pass parameters, what are we going to use to pass parameters? I'm gonna let you guys guess before I switch the screen back to the agreement, because the answer is over there. All right, somebody's guessing. Locations in RAM, that is correct, but what kind of locations in RAM? In other words, how do we organize those locations in RAM? The ordering of storing and retrieving. It's the one thing. It does relate to register D, okay? Well, register D is our stack pointer, right? So we are actually using the stack to pass parameters, okay? So this looks kind of strange, right? So let's go ahead and take a look at another subroutine. So I'm going to continue on this side here, and we'll use another totally useless subroutine, and we'll call it add, okay? And all it does is to take 2 parameters, add the 2 parameters, and then return the value of the 2 parameters. Let me think. I think we can do better than that. Let's not use add. Let's just use something that you are really familiar with already. Absolute value. Okay, this is something that we have done already. So we say it takes one 8-bit signed integer as x, and then in here, I thought somebody else was typing a little bit earlier. So if you have a question, don't hesitate to type, even when I'm, talking about something else. All right, so in here, we're gonna do an if statement. So this is the longer version of absolute value. So there are several ways to do this, okay? The C code is going to look kind of cumbersome regardless of what we are going to do. We can do the usual return. This is the one that you're familiar with. So if x is in fact less than 0, we return the arithmetic negation of x. Otherwise, we return x itself as the return value. So I believe all of you are somewhat familiar with this code because we have done it, okay, in one of our labs. So now the question is, how do we do this in a subroutine? So let's go ahead and use ABS to start up the beginning part of the subroutine. So the agreement in this case is the caller would push arguments on the stack, and then the return address on the stack. So that means on the stack, what we can expect, from the perspective of a subroutine, is the register D, being the stack pointer, is pointing to the very last thing that the caller pushed on the stack, which is the return address. Okay, but we can also make the assumption that before the return address was pushed on the stack, parameter X was pushed on the stack first. So this is how we can look at the stack at the very beginning of the subroutine absolute value. So what this means, okay, is if return address is at location, we'll call it L, okay, then X as a parameter is at location L plus 1 on the stack. Is that okay? Now, if you're having some, problem understanding this, it's okay for now, because we'll actually run this code with a proper caller, and then we'll actually run it through the trace analyzer, after we run the program. Okay. I think about. Okay. All right. All right, so what do we do at this point? How do we get back to X? Okay, that becomes the question. All right. I'm not really sure what we want to confirm. Okay, Catherine or Richard, can you guys clarify? The position on the stack, yes. So X is at a higher location, which is exactly just 1 byte higher compared to the return address. Now this has to do with the stack is growing, quote unquote, down. Okay, when the stack is empty, the stack pointer points to the highest location, which is 1 byte past the actual end of the stack. And as we push items on the stack, the first thing we do with every push operation is to decrement the stack pointer first, and then we store to where the stack pointer points to. So that is why X being pushed first is at a higher byte location compared to the return address. Okay, so based on what we can see about this, we can do this code using this particular way. So we use a CPR, which is a copy register, and we'll copy register D to register C. Okay, so I always write next to the line. Well, not always, but most of the time I do this. I kind of comment on what the mnemonic is actually doing. So at this point, both register C and register D are pointing to exactly the same place on the stack. They're both pointing to the return address, which is not very helpful in implementing this code here, because I don't need the return address right now. I'm not at the end of the execution of the program. I just need to get to parameter X at this point. So what we do after that is we can increment register C. So now C is actually D plus 1, or the value of D plus 1, which turns out to be the address of parameter X. So are we still doing okay at this point? And I should probably use double equal here, because I just want to state the condition. I'm not trying to specify the operation. So are we still doing okay up to line 13? All right, kind of. Okay. So we can when we get to the trace analyzer after running this code in Logisim, it will be very, very clear what we are dealing with. Okay. So now the C is the address of parameter X. We go like, but this code is not asking for the address of X, it's asking for the value of X. So what can we do to get to the value of X? Which instruction should I use? Dereference, exactly. And we are reading from RAM, right? There are only 2 instructions that would do any type of explicit dereferencing. One is load and one is store. Okay, That makes it very easy to remember, to choose, because now that we need to dereference, you have to choose either LD or you have to choose ST. So which one should we use? LD, indeed, because we are reading from RAM, we are not storing to RAM. So LD, which is also the same as read, okay, load is the same as read from RAM. So what we do is we load, let's use another register, which I don't really need to. I can reuse register C, but if I want to make this really obvious in the trace, I can keep register C as the pointer, and now I use register A as the value at of the location that register C is pointing to. So now we say A is the dereference of D, oops, not D, C, which is the dereference of the address of X. Can someone help me simplify this thing? The dereference of the address of X. Is there an easier way to specify that? I'm talking about this expression here. Yep, it really is just X. Okay, in C, C++, and the syntax of most programming languages, it simply is just the value of X. All right, so now that we have the value of X, we can now just slap in the code that you have done already, to check whether X is negative or not. If so, we perform a 2's complement and blah, 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 right? So we can do that really quickly here. So we use AND AA to test, A, and then we use a JSI, okay? In this case, we have to use JSI, cannot use JOI or JLI because we are not actually comparing, okay? We are simply running register A through the ALU to set the flags register, okay? And we're only paying attention to one of the flags, which is the sign flag, so that we can tell whether register A has a value that is negative or not. We are looking at the sign bit, so here we say X is negative, and I usually just define it right away. X is negative, and then I put comments, that is based on the continuation. So this means X is not negative, and over here it means X is negative. Okay, now it seems pretty kind of time consuming and unnecessary to comment like this, but if you don't do something like this and your program gets longer and longer and longer, by the time you get to a label, you would have forgotten what that label is representing and what you're supposed to do at that label. So this is what I do, and I have been doing this, since I would say maybe the early 90s. And it has helped me tremendously, okay, just so that I can remember by the time I get to a particular label, what does it mean? What am I supposed to do at that point? All right, so if X is not negative, well, guess what? Register A really is the return value already. So now I can just go to a continuation label, and we can just say that ABS is ready to return. I'm using these kind of stupidly long label names because they're self-documenting. All right, so we'll define it over here. ABS as the name of a subroutine is ready to return, and this is why I like NVim, with a particular extension. It remembers what kind of labels I have defined or what kind of names I have used. So I can just, if I just type the beginning part of a name, it will give me a prompter. So I can just select that one and then press the Enter key, and I don't have to type, a whole lot. All right, so now the question is, what if it is negative? Well, we know how to do this already. We have to perform 2's complement, which involves 1's complement, which is a bitwise NOT, and then +1, which is an increment instruction. That's it. Okay. So by the time we get to ABS is ready to return, register A already has the correct return value. So what is left to do is just to perform the code to actually return it. Okay. And this one is done by LD. I can reuse register C if I want to. I can use register B if I want to. So this is another point that is really important, is the caller cannot assume a subroutine will preserve the value of any of the registers. Okay, So let me say that one more time. If a caller is calling a subroutine, the caller basically has to assume the subroutine will modify all the registers A, B, and C. Okay. Now register D is a little bit special, okay, because the caller can assume register D to be modified in a very specific way, which is what we're going to do here. So I can now load the return address into register B, increment the stack pointer because that location on the stack is no longer useful anymore, and then JMPB. That's all we need to do. But then there's a question, right? Because from the comment here on line 9, we are taking care of the deallocation of the return address on line 25. But what about the parameter? What about the parameter which was also pushed by the caller? As it turns out, the deallocation of items on the stack is a split job between the callee and the caller. The callee is only responsible to deallocate the return address. That's it. The caller, on the other hand, is responsible to deallocate all of the arguments. And because we are looking at the code of the callee, so the deallocation of x, the parameter x, is not seen here because it is not done by the callee. All right. So we still doing okay at this point. All right, cool. So now we will try to look at things from the perspective of the caller. So we'll write another subroutine here, which is the caller. And we'll say void, okay? So this one does not return a particular value because we just want to kind of check things out, okay? So it's a void. And we'll say test, okay? And takes no parameters. And the only thing it does is to call ABS, and we'll give it a constant at this point, and then later on we'll make it a little bit more interesting. But at this point we just give it a constant, okay, say -5, okay, and that's it. And somebody's going to point out and go like, but that's totally useless because nobody is using the return value of ABS. So what is the whole point of doing this? Well, the whole point of doing this is really just to illustrate how we set up the passing of arguments on the stack. But if this is the case, we cannot even tell whether the program is working correctly or not. You would be correct if you're thinking that, okay? In the C code, if you're running this in C, even in GDB, you can, but it's really difficult to see that this code is doing it correctly. But when we look at the assembly code, and we are running the assembly code in CLI mode with the trace and the trace analyzer, we can actually tell whether the program is working correctly or not. Okay, so that's why we are going to switch back to the assembly code, and this time we are looking at the subroutine test. So subroutine test is relatively simple because it has no parameters, so I don't really have to look at what the stack would look like at the entry point of test. And we also don't have to pay attention to, do we need to use register A to specify a return value? Because test does not return a particular value. So that means I can actually use register A, in the return code. Now, there's no need to do something like this, okay? Register A in this case is not special in any way. So I could have just used register B to specify the return, to use register A, I could have used register B to store the location where I'm supposed to return to, but I just want to illustrate that we could have done this, okay? Because register A is not special in this case, test has no return value. So now the question is, how do I make that call, okay? So this is where I will introduce something that is a little bit new, okay? But we'll do it the old way first. So doing this the old way means, we have to use a label to label where the subroutine is supposed to continue execution when it's all done. So we'll say this is test return point 1, okay? Because just in case I want to do another call, we'll have a return point 2. So this is where the subroutine is supposed to get back to when we're all done. So now the question is, what do we do before we get here? Now we know the very last thing we do before we get to the label of line 30 is we just want to continue execution at ABS. Okay, I'm writing the program backwards. Okay, by the way. But before that, I also know that the very last thing I need to do is to push the return address on the stack, right? So to push the return address, which is represented by the label test return point 1, I need to load it into a register. Now register A really is not special, at this point, so I can definitely keep using register A. Test return point 1. Then we have to push it on the stack. The sequence of instructions to push is to first start with a decrement D to allocate a byte on the stack, then use that location that we have just allocated to store the return address, which is in register A at this point. So these 3 lines of code, lines 29 to 31 at this point, is for pushing the return address on the stack. But wait, there's something else that we should have done before this, because we have an argument of -5. So this is new because we are now saying, oh, so that means we have to push -5 on the stack too before we push the return address, because that is the agreement. Okay, the agreement between the caller and the callee is the caller would push all the arguments, then the return address on the stack. So now we have to push the -5 on the stack, which is going to be relatively simple. If I were super lazy, I would have just done something like this. Okay, copy 3 lines of code, paste it, change the label to -5. This has been verified to work. You can actually specify -5 as a constant, and it will load. In this case, I think it's FB, in hexadecimal into register A, because that's how -5 as a value is represented as an 8-bit signed integer. So now we have all this code almost done, except for one little thing. That one little thing that we haven't done yet. Okay, if I were to run this code, it's not going to do it correctly. Okay, so maybe I shouldn't fix that problem and just let the program not do what it is supposed to, and then we'll figure out how to debug this program. Okay, there's one little thing, okay, just one single instruction. It looks super innocent that I did not do, that I mentioned earlier. Okay, but it's going to cause this program not to work. But that's okay. We'll figure it out. So at the very beginning of the program, we'll put a no op, because every program that you want to run through the CLI mode of Logisim needs to start with a no op. And we can either specify main over here, or we can do a JMPI to main, which is what I will do here. Okay, so I'm going to JMPI to main, simply because the C code is going to structure somewhat like that. So now we got main over here, and let me go back to the C code. So in the C code, we have int main, and main is going to call test. That's all it's going to do, call test and return 0. That's the entire program. So in assembly code, we have something similar. I need to do a LDI a, so this time I'm not predefining the label, main return point 1, decrement D, then we have store to whatever D is pointing to, the label, continue execution at the subroutine test, and when the subroutine is done, in the C code we have a return 0 from main. But remember, in assembly code in the TTP ASM environment, main has no operating system to return to. There's no pre-C code to return to. So all we really can do is a halt instruction here to say that, yep, we are all done. Okay, so stop the trace. All right, so we're going to go ahead and test this program. Okay, and we already know that this program is not correct. Okay, remember what I said earlier, I intentionally missed out one little thing. So we're going to take a look at this program and figure out, which part works correctly, and we'll observe that it works correctly. And then we'll look at the part that it does not work correctly, and then we'll say, that is not normal. That doesn't look right to us. Okay. All right. So that's what we'll do. And now I have to copy this into the clipboard. Okay. So we'll go ahead and cat return value TTPASM and pipe it to xclip cell clip here. And then we can switch back to the assembler. Go back to the source tab, get rid of the old program, and paste this new program in. And then go to RAM file, and there are errors. Okay, so what did I miss? Unresolved. Oh, okay, that's right. All right, so this is good. Okay, so that means certain errors we can fix in, it can be detected at least by the assembler. So we now switch back to the editor. Can someone tell me where main return point 1, where should it be defined? Give me, the line number. We kind of know that it has to do with maybe right after 47, maybe right after 48. Yep, it should be the new line 49. Richard is correct. Okay, so here is where I need to define main return point 1, because what this label is doing, its job is to say, oh, I'm just a symbolic name representing the address of the halt instruction. So when the subroutine test is all done, when it returns, we want to return to the halt instruction on line 50 so that we can say the program is all done. Okay, so Richard is correct. So we'll save it, and then we'll go ahead and copy this again. So we cat return value.ttpsm to xclip cell clip. There we go. And then we go back to the assembler and then paste it in again. And go to RAM file, and everything is good this time. All right. So we have a lot of comments at the very beginning, and that's why we don't see a whole lot of code at the beginning, because I pasted in the wrong part of the spreadsheet. I totally ignored the first 37 lines of the spreadsheet. It still works, okay? It's just that that's why in the RAM file we have a whole bunch of blank lines until we get to line 38. So that's okay. It still works. It's not a problem. It just looks kind of funny. So now we switch back to the command line, and we'll go ahead and save all. Okay. Oh, okay. Actually, I think it's XA to save everything. So now we can go ahead and run Logisim again. Okay, so here, this is how we run Logisim, but we are no longer using stack.csv. In fact, we haven't downloaded the RAM file yet. So let me switch back to the assembler and download the RAM file first. So download CSV, and how should we call this? Return val, okay, rutval.csv, and then we switch back to the command line, return val, and I'll change the tsv file as well to return val. So this way, we have one trace file for each program. Press the enter key, and it's all done. Okay. Now sometimes you can run into an infinite loop and it doesn't stop. Now if it doesn't stop within a reasonable amount of time, you can type Control-C on the keyboard in the CLI to stop it. So in that case, you will still end up with a trace, but that trace will not end with a halt instruction, because somehow the program has an infinite loop and it never got to the halt instruction. Okay, so now we switch back to the browser. Oops, that's the wrong one. And that's the right one. There we go. So now we go to the trace analyzer. Remember to switch back to sheet 1 first. And also, remember when you import, you're importing the trace file that we generated earlier from running Logisim on the command line. And in this case, it's return value.tsv. All right, so that, and that. So it takes a little bit of time to kind of crunch through all the zeros and ones. But once it's all done, we get into here. So there are several critical points that we need to kind of take a look at. So if I were to go back to the source code, okay, and the assemble tab is really the best. It gives you the most amount of information that is relevant to debugging a program. So let's go to line 37, okay. So line 37 is a no op, obviously not very interesting. Line 38 is just continuing execution at the label main. And the label main is over here. Line 81 to line 84 is for calling the test subroutine. So then we get to the test subroutine. The test subroutine is going to push -5 on the stack using line 68 to line 70. It will push the return address from line 71 to line 73, and then it continues execution at the subroutine called ABS on line 74. So we probably want to, look at what's happening right about at this point here. Okay, what happens when we try to push -5 on the stack? Okay, so this is what we'll do in the trace analyzer. So here's the trace analyzer, and we want to stop at location, or we want to start paying attention when the program counter is at 15 in hexadecimal. So we go to the trace analyzer, and we just focus on column A until it is 15, which is right here. All right, so at location 15, we put -5 as a bit pattern into register A, and that's why A ends up with a value of FB in hexadecimal, because that's how -5 is represented as an 8-bit signed integer. On line 17, we decrement the stack pointer to basically reserve another spot on the stack, and so the stack pointer is decremented from FF to FE. So now someone may be asking, so what did we use location FF for? Can someone answer that question? By the way, we are currently in test as a subroutine. So what do you think location FF on the stack is being used for? Nope. We have not yet pushed FB on the stack. So FB is still sitting just in a register. So something else was using location FF. What used up location FF? Remember, test is a subroutine. Main calls test. So when we're calling a subroutine, what is going to use up the stack? Main is the caller. Test is the subroutine. We're currently in the subroutine, which means main has already made the call to test. And as a part of calling a subroutine, it's the return address that we have pushed. It is the return location. It is the return address to main that is now sitting on the stack. All right. Well, if that is the case, we should be able to see it in the trace, right? And the answer is, yeah, we should be able to see it. This is it. We wrote to location FF in RAM, and we put the content or the value of 28 in hexadecimal to location FF. So that means if my theory is right, okay, 28 should be the address of where we should return to in main when test is done, right? So how do we know that is the case or not? We go back to the assembler, and then we continue into main at this point, and we look at the label definition of main return point 1, and it is indeed 28 in hexadecimal. It's 40 in decimal, but 40 in decimal is 28 in hexadecimal. So the trace analyzer is confirming that we pushed the return address back to main correctly on the stack. Okay, so that's good. So now location, So location FB is, excuse me, the value FB is stored at location FE, which is 1 byte below the return address back to main. Then we also have to push the return address back to test itself, because test is calling ABS. So as a part of calling a subroutine, test also needs to push its own return address on the stack after pushing its argument on the stack. So that's why we use 1F, because if we go back to the assembler, we can see that 1F is test return point 1, which is where ABS is supposed to go back to when it is done. So this is location 1F. It is right after test return point 1 inside the test subroutine itself, so that we can continue execution in the caller when ABS is done. Okay, so when we look at the trace analyzer, everything is good up to this point. Okay, it's all good. Then we get to location 1B, and location 1B is where we push the return address. This is where we decrement the stack pointer, and then after we decrement the stack pointer, we store to the location that we just reserved on the stack, and we're going to store the return address back to test, which is known as the label test return point 1 on the stack. And then after that, we have a unconditional branch to the subroutine. So 1D is the JMPI instruction. It is a unconditional branch instruction, so that we continue execution at location 08, which is the beginning of the subroutine at ABS. The absolute value subroutine is starting at location 08. So are we still doing okay at this point? Does anyone need a short break or clarifications? We're about 15 minutes to the end of the lecture, so yeah, maybe not really a short break. Oh, okay. Yep. Yep. Rewatching, is usually helpful, because you can pause and then you can start to jot down notes, and also, and by the way, you guys can make a copy of the trace analyzer and also the assembler right now at this point, and then just rename it to return value. Okay, so this way you have a snapshot of not only the program, which is in the assembler spreadsheet, but also the trace corresponding to it, and you don't have to go through the CLI stuff that I did, and you can just look at it. So you might want to do that if you kind of want to save yourself some time, so that you don't have to do it. So now we are at location 08, okay, and in the assembler, if I look up the location 08, this is location 08, and what exactly is it? It is indeed corresponding to ABS. Okay, so we are now at the entry point of ABS, and this actually is where things start to get interesting. Okay, so the first thing we do inside ABS is we make a copy of the register D in register C, so they both point to the same place. So in the trace, when we look at what we do at location 08, so at 08, we can see that now register C also has a value of FD. But remember, register D already has a value of FD, so this makes sense because we're just copying register D to register C. So now register D and register C are both pointing to location FD on the stack, which has the return address. Now, how do we know it has a return address? Because this is what we put over there earlier, okay? And 1F was, identified as the return address, from ABS back to test. So now what do we do? Well, we increment register C by 1. So this is C after the increment. It is now pointing to location FE, which is where the parameter is. How do we know that? Well, if we look back to here, we can see that FB is the value at location FE, and FB is the 2's complement of 5. So that's -5. So now we know that register C is now the address of the parameter. The next instruction of 0A is a dereference. We are using an LD instruction to load whatever content is at location FE into register A. So now register A has the content of FB. All right. Now we move on, which is a test instruction, the AND AA instruction. So the AND AA instruction is basically just passing the bit pattern of FB in hexadecimal through the ALU so that we can set a few flags. Once again, the L flag is not important in this case, so ignore that. Only the sign flag is important in this case, and the sign flag is a 1. So when we get to 0C, location 0C, which is our JSI instruction, is conditional, which basically means we only want to branch if and only if the sign flag is a 1. It's a JSI instruction. So it did branch this time, so 0C branches to 1, 0. And in the assembler, we can also see how it works. This is location 0C. And after we execute the instruction at location 0C, we end up at location 10. But location 10 is right at the label of X is negative. So we did branch, because if we did not branch, we would have ended up at location 0E instead of 10. So at location 10 in the trace, we perform a bitwise NOT. So the bitwise NOT, is the bitwise NOT of FB. FB is 1111, and then we have a 1011. Okay, that one single 0 is turned into a 1, and then all the ones were turned into zeros, and that's how we end up with register A having 04 in it, because 04 in binary is 0000 0100. So that is correct. Okay, so if you take the bitwise NOT of FB, you end up with a bit pattern of 0A in hexadecimal. But remember, 2's complement is called 2's complement because it is 1's complement, which is the same as bitwise NOT plus 1. So this is where the plus 1 is. And then after that, we perform the return operation. The return operation starts with retrieving whatever the stack pointer points to into register B. So register B now has a value of 1F, which is where we need to go to continue execution in test, because test is the caller of ABS. And then we increment the stack pointer, because remember, the agreement is the subroutine is responsible to deallocate the return address on the stack. And then on line 14, we have the JMP B instruction. So whatever register B has now becomes the program counter, and that's why the next instruction that we execute is at location 1F. At location 1F, let's see what we're doing, because this is where things should start to go wrong. So at location 0F, okay, oh, 1F, sorry. So at location 1F, we are now saying, I think the stack pointer should now point to the return address so that I can return from test back to main. Well, hold on a second here. Is that really the case? The stack pointer at this point, okay, when we are at location 1F, what is the stack pointer? What is the value of register D? All we have to do is to track down register D in column D. So register D is now FE. If you were to draw a map, okay, which is something that I highly recommend all of you to do, is either to hand draw a map or you can use a spreadsheet so you can keep track of which location of RAM is doing what, okay? But location FE is not where the return address is. Location FE is where the argument is when we called ABS. When test calls ABS, it has to pass -5 on the stack. That -5, or the bit pattern of FB, is exactly where FE is. So now we are basically using an argument as a return address. So when you look at the code here, when we get to location 1F, it is using whatever the stack point is pointing to and wrongfully in this case assume that the stack pointer is now pointing to the return address, but in reality it is actually pointing to the argument that we have set up earlier in order to call ABS. So what's going to happen when the program has a flaw like this? The trace analyzer is very helpful in this case. So at location 1F, we retrieve that value that the stack pointer is pointing to into register A. Then we proceed to deallocate that location on the stack. Then at location 2-1, we have a JMP A instruction, which is basically just using whatever register A has and say, well, whatever register A has is where we're going to go to continue execution. So now it's continuing execution at location FB. Whoopsie, right? That's not good because FB is currently just some RAM location sitting in La La Land. Okay, this is in La La Land. It is not even part of the stack that we have put values into. It is just sitting somewhere in RAM, and because when we reset the processor, everything starts with 0 in RAM, so location FB has 0, 0. Can someone tell me what is 0, 0 is the opcode of which instruction? The no op instruction. Very good. So the no op instruction says, I'm not going to do anything other than just incrementing the program counter so we are ready for the next location, which is FC. FC is also not used in this program at all, okay? Which means it is quote unquote reset to 0, 0 at the very beginning, which is also a no op. So FC being a no op says, I'm not going to do anything. I'm just going to increment the program counter until we get to FD. But FD is not 0, 0 because we wrote to FD earlier. Okay, if I could just scroll back, FD has got the content of 1F. Okay, so now the question is, F1F as an opcode, what operation, which instruction is it mapping to? So we are basically doing what the assembler, we're doing the reverse of what the assembler does. The assembler starts with mnemonic and it converts the mnemonic into opcode. So we are looking at an opcode and we are trying to say, well, if we were to try to execute the opcode at location FD, which instruction is corresponding to it? And you will find that there are no instructions corresponding to it. Okay, and the best way to illustrate that is to, let me go back to my command line here, is to run logisim without using the command line options. Okay, so we'll just do this part and we'll manually load, actually we don't even need to do that. The opcode is supposed to be 1F, so now we need to look in the ROM and go to location 1F0 because we know that location is of interest to us because we know that would correspond to the microcode for the opcode 1F. So 1F0 is right here. It has a slice of all zeros. Can someone kind of remind me which known mnemonic has an opcode where the only microcode slice are all zeros? We have encountered exactly one single instruction that has a microcode slice that is all zeros. Which one is it? Not quite reset. It's kind of the opposite of reset. Halt, that's right. So the halt instruction, the mnemonic HALT, translates to opcode 01. So that means the microcode slice, or the first slice of microcode corresponding to halt is right here. They're all zeros. And I have already explained in the previous class how, if the microcode are all zeros, it's basically it keeps reloading whatever bit pattern is in the instruction register into the microcode pointer. So that's why now the ROM is stuck in an infinite loop. When we have something like this, okay, when the instruction register has one F in it, and then the microcode slides at this location are all zeros, it will do exactly the same thing. In other words, it's going to go back to the microcode pointer, will basically reload itself with one F0 over and over and over again. In other words, it's basically achieving the same thing as a halt instruction, even though it is quote unquote a different opcode. So with all of these zeros, okay, 030, 040, 050, if you see all zeros as the first location of an address that is divisible by 16, all of those locations are corresponding to the same thing as a halt instruction. They're basically just instructions, they're basically just opcodes that are unused by the toy processor at this point. So that is why the program actually stopped, because any one of those locations would equal to 0, or the ROM output would equal to 0. So when this comparator sets the output of the ROM, if it is 0, then it will set this particular output pin, labeled halt, to a 1. This is how the CLI mode of Logisim knows when to stop. Okay, it will stop as soon as the output of ROM, the D port of ROM, are all zeros. And that's why the program actually stopped, even though it was incorrect. So we're almost out of time, and it is probably a good idea for me to fix the program so that you know where we are supposed to change and how to change it. So let me, okay, so let me go back to Logisim first, because I can close it at this point. And then we'll go back to the program and fix that location. The C code is not wrong, okay? It is the assembly code that is wrong. So the problem is right here, okay? Right after we get back from ABS into test, test as a caller has one extra thing to do. It pushed the -5 on the stack as an argument, then it pushed the return address on the stack, and then it continues execution in the subroutine called ABS. When ABS returns, the caller says, I can assume the callee ABS is deallocating the return address. But what about the argument? What about the -5 that is still sitting on the stack? That is the responsibility of the caller, which is test itself, to deallocate. So right here, we need to increment D. This is the key to fix that problem, to deallocate -5 as an argument on the stack. Okay, so this will fix the problem. Okay, I'm not gonna rerun the program after I fix it. What I can do is I can post the C code and also the assembly code onto Discord so that you guys can download it. And if you want to play with it, go ahead. If you want to annotate and document it, go ahead. Okay, and I think that is a great idea. Okay, because I did not document a whole lot. I documented a little bit in this code. So as you re-watch the video of today's lecture, you might want to consider pausing. When I explain a certain thing, go into the source code of return value.ttp ASM, and then use your own words to document what a particular line is doing, or what you have understood about this program, and put it into the source code itself. So that is, one of the recommendations. Okay, whether you want to do or not is entirely up to you. So let me just post it on Discord right now. Okay, I'll give you both the C code and the assembly code. The C code is not particularly useful, but the assembly code is probably more useful. So let's see, it's return value.ttp ASM. Nope, it's not in that folder. What is the parent folder here? PWD, print. No, it is in the right folder. Try that one more time. So this is the .c file, the C code, and here's the corrected version of the assembly code. All right. So both of these are now on Discord, and I'll go ahead and pin it. So this way, if you don't want to read through all the messages, you can just go straight to the file download. Okay. And I have already mentioned that you can make copies of the assembler and also the trace analyzer at this point. And I'm not going to touch it, okay, for maybe the next hour or so. So you got a little bit of time to, if you want to take a snapshot of it, you can. And now I need to give you guys the lab, okay? So the lab today is about what I just mentioned. It is all about returning values and passing arguments to subroutines. So, and it's already set up. I just need to give you the passcode to it so that you guys can get started with it. And it is right here. It's called parameters and return value. And the passcode is frame. There we go. There's a particular reason why it's called frame. If you remember, frame is also a command in GDB. What a frame is representing is everything that is relevant to a particular invocation of a subroutine on the stack. So when you look at all the arguments that are pushed on the stack and the return address, and also the local variables of a particular subroutine, that contiguous chunk of memory on the stack is called a frame. So every invocation of a subroutine has a frame. If you're talking about a recursive subroutine, then you can have multiple frames corresponding to the same subroutine on the stack at exactly the same time, because those particular frames, each one is representing a different invocation of the subroutine. So we'll talk about those concepts, maybe tomorrow, because recursion is interesting in a way, but once you know how recursion is implemented in assembly, that should take away all the mysteries corresponding to recursion. All right. So do we have any questions before I stop live streaming? I'll let you guys have some time to ask before I stop here. Not seeing anything. All right, so I'm just gonna quickly go through all the questions. So the questions resemble a lot of the lecture material that we talk about today, how to return a value, how to utilize a value in a caller, and how we pass a single parameter. And then we talk about how to access a parameter from inside a subroutine. And then it talks about how to pass multiple parameters. So when we pass multiple parameters, it's a very counterintuitive standard, because the way we do this, okay, when we pass multiple parameters, is we push the last parameter first. That's it. The first parameter is pushed last, or the last parameter is pushed first. So this is an example to illustrate when we have three parameters, 2, 3, and 4. The way we push the arguments on the stack is we first push the 4, then we push the 3, then we push the 2. So when we access these parameters from a subroutine, 2 in this case is the one that has the lowest address on the stack, then 3, and then the 4. Okay? So that's basically one little thing that we didn't talk about in class, but for the rest, they're all basically stuff that we have already talked about in class. So I don't think today's lab is going to take up too much time. I don't think you have to write any code in this particular lab. So it's really mostly just concept questions. And you can retake it as many times as you want to. All right, so I'm not seeing any questions in Discord. So I'm gonna get out of live stream mode. So I'll be looking at the text channels at this point. If you guys have any questions, do not hesitate to ask in the text channels.